All right, today we're going to break down one of the absolute fundamentals of computer science, selection sort. If you've ever wondered how a computer takes a totally jumbled mess and turns it into a perfectly ordered list, well, this is one of the first, simplest ways it can happen.
I mean, think about it. If someone handed you a stack of cards with numbers on them, all mixed up, how would you sort them? You'd probably scan through, find the very smallest number, pull it out, and put it on the left, right? Then you'd look at the rest of the pile, find the next smallest, and place it right next to the first one.
And guess what? That incredibly human, super intuitive process you just imagined, that's pretty much exactly what selection sort does. It's one of the simplest sorting algorithms to wrap your head around, which makes it the absolute perfect place to start. So, let's dive in.
So what is this thing really? What's the core idea behind selection sort?
Okay, a really key phrase here is in place. All that means is the algorithm is smart enough to sort the list without having to create a whole new copy. It just shuffles the items around right where they are, which is fantastic for saving memory. The logic is as simple as it gets. Find the smallest thing and move it to the front. That's it.
The easiest way to picture this is to imagine the list is split into two parts. On the left, you've got your sorted section, which starts off completely empty, and on the right, you've got the entire unsorted mess. With every single step, the algorithm scans the mess on the right, selects the smallest item it can find, and moves it over to the end of the sorted list on the left. The sorted part grows, the unsorted part shrinks, one element at a time.
Theory is great, but seeing is believing, right? Let's actually watch how this works with a visual walkthrough.
So here's the whole process laid out, from the messy beginning to the perfectly sorted end. You can see how with each pass, another number finds its final home. Now, let's slow it down and trace the logic, step by step.
All right, follow along with me here. We start with our list, 3, 6, 8, 4, 5. On the first pass, we look through the whole thing. The smallest number is 3. Well, hey, it's already in the first spot, so we don't have to do anything. The sorted part is now just 3. Cool. Now for pass 2, we ignore the 3 and look at the rest. 6, 8, 4, 5. The smallest in that bunch is 4, so we swap it with the first unsorted number, which is 6. The list is now 3, 4, 8, 6, 5. You see the pattern? We just keep going. Next unsorted part is 8, 6, 5. The smallest is 5, so we swap it with the 8. And just like that, the whole thing is sorted. Simple and very methodical.
Now that simplicity is beautiful, isn't it? But it comes at a cost. And now we have to talk about performance, or what I like to call the price of simplicity.
To talk about performance like a pro, we use something called Big O notation. Now, don't let the name scare you. It's actually a really simple idea. It's just a way of asking, if I make my list twice as big or 100 times bigger, how much longer is this going to take? It's all about how well the algorithm scales.
And this chart really shows you why that question matters. The difference in growth is, well, it's huge. A linear algorithm, O of n, is predictable. You double the data, it takes about double the time. But a quadratic one, O of n squared, that thing just explodes. You double the data, and it takes 4 times as long. For big lists, that's a total deal breaker.
And yep, you guessed it, selection sort is O of n squared, or quadratic, and that's its single biggest weakness. Why? Well, think about it. For every single element in the list, we have to scan through all the remaining elements to find the minimum. That's a loop inside of a loop, and that is the classic recipe for quadratic performance.
And what's really kind of wild is that its performance is O of n squared across the board. Best case, worst case, average, it doesn't matter. You could literally hand it a list that's already perfectly sorted, and it's still going to stubbornly check every single element on every single pass. We say it's not adaptive. It just does the same brute force amount of work no matter what.
But there is a massive silver lining. Its space complexity is O of 1, or constant space. Remember how we said it was in place? This is the payoff. It only needs a tiny, fixed amount of extra memory to do its job. It doesn't matter if you're sorting 10 items or 10 million. That is incredibly memory efficient.
Okay, so we've got this fascinating trade-off, right? It's slow, but it's simple and sips memory. Which brings us to the final verdict. When would you actually use this thing in the real world?
Let's recap the good stuff. First, it's incredibly easy to understand and implement. It's a fantastic teaching tool. Second, that O of 1 space complexity is a lifesaver in situations where memory is tight. And third, and this is a sneaky one that's super important, it performs the absolute minimum number of swaps possible. It only moves an item once it's found its final resting place. If writing to memory is a slow and painful operation on your system, that is a huge, huge win.
Now, for the bad. That O of n squared time complexity is a killer. For any large list, it's just way too slow. It's also not adaptive, as we saw. And finally, it's what we call unstable. All that means is if you have two identical items, like two number 5s, it doesn't guarantee they'll stay in their original order. Sometimes that matters, sometimes it doesn't, but it's a detail worth knowing.
So what's the bottom line? Selection sort has its special moments to shine. It's the perfect tool when you're sorting a small list, think less than 50 items, and raw speed just isn't your main concern. It's a great choice when memory is at an absolute premium. And it's an excellent option when writing to memory is expensive, like with some kinds of flash storage. And of course, it's the perfect first sorting algorithm to learn when you're starting out.
And that kind of leaves us with one last big thought. We've seen that selection sort's beautiful simplicity comes at the very steep price of speed. So it begs the question, if this is what simplicity looks like, what does true, raw, unadulterated efficiency look like? What does it take to sort millions of items in a flash? Well, that's where you get into amazing algorithms like quicksort and merge sort. But that's a story for another explainer.